Okay, so this is the chapter 1A. We've split chapter 1 into two sections. So we'll have a chapter 1B coming up, but this is for our first test on chapter 1. So question 1, this section we are determining whether each relation is a function. You're going to write yes or no and tell me why. So first we have this mapping diagram. We notice, like if we wrote these as, oops, that is not the first thing we have. First, we have the ordered pairs. So we're going to look at the x inputs. And we have no repeats, meaning that this is a function. So yes, because there are no repeated x values. And then if we look at number 2, the mapping diagram, if we wrote these as ordered pairs, A goes with X, A also goes with Z, and then B goes with Y. And because we have a repeat of an input value, this is not a function because the A is paired with 2 outputs. Okay, number 3, we have a graph, so we can just look at vertical line test, and we have no issues at all along the entire domain of this graph. So this is yes, a function, because it passes the vertical line test. Okay, next section, we are finding the values of each function at the given point. So we are going to take the given value and plug it in to our function. So g of 8, plug in an 8 wherever we see an x, would be negative 8 squared plus 9 times 8 minus 1. So square 8 is 64, put the negative sign out in front. Negative 64, 9 times 8, 72, minus 1. So when we do all of that together, that equals positive 7. So g of 8 is 7. Okay, g of negative 2. We're going to plug in a negative 2 wherever we see an x. Be super careful about your order of operations here. First, I have to do this, exponents first. So you cannot decide like, oh, it's a negative negative, I'm going to make it a positive. First, you must do your exponent. So we get negative 2 squared is 4. We tack on that negative sign from out front. 9 times negative 2 is negative 18 minus 1, which gets us negative 23. And then finally, we have 4x. So if we do g of 4x, we're going to plug in a 4x wherever we see an x value. So 4x squared plus 9, plug in 4x for x, minus 1. Be careful when you do this. You must distribute the exponent to both terms. So we get negative 16x squared. So we square the 4 and we square the x. Plus 9 times 4x is 36x minus 1. We cannot simplify this any further because we have no like terms to combine. So g of 4x is negative 16x squared plus 36x minus 1. All right. Domain and range of functions. We're going to find the zeros, the y-intercept, and then the domain and range of each function. So starting with this, f of x equals x squared minus 7x minus 18. This is quadratic. So we know it's going to have this parabolic shape. And it's going to be concave up because we have a positive a value. All right, to find the zeros, we factor. So negative 18 on top, negative 7 on the bottom. This is going to be negative 9 and 2. X minus 9, x plus 2. Set each of these equal to 0 and solve, and those will be our zeros. So x will equal 9, and x will equal negative 2. Okay, the y-intercept, we can see that because it is in standard form, so we know our y-intercept occurs at negative 18. Our domain for all quadratics, because it is going upward and outward to infinity, is from negative infinity to positive infinity, so all real numbers. To find the range, we must find the vertex of this function. So we need to figure out the y value of the vertex in order to decide exactly what our range is going to be. So because we have standard form, we know that x equals negative b over 2a. So I plug that in. Negative b is negative negative 7 over 2 times 1. So x equals negative 7 halves. So the x of our vertex, not negative 7 halves, positive 7 halves. But I need the y coordinate of my vertex in order to determine the range. So I get to plug in my fraction value to my original function. I'm going to do that over here. So we get 7 over 2 squared minus 7 times 7 over 2 minus 18. On your quiz, you can, or on your test, you can expect to see a fraction like this, and I will expect to see a fraction in your answer rather than a decimal. I do not ever want to see repeating decimals or um, like irrational decimals. My hope is that you will figure out the fractions. So squaring, we square the top and the bottom. So this becomes 49 over 4. This is technically 7 over 1. So multiply straight across. 7 times 7 is 49. 1 times 2 is 2 minus 18. And this is technically over 1. So then we get a common denominator. The least common denominator for each of these is 4. So we would multiply top and bottom of our second term by 2, which would give me 98 over 4. And then we would multiply top and bottom by 4 in order to get to our common denominator of 4. So 18 times 4 is 72. Then we're just going to do our subtraction. 49 minus 98 minus 72 is negative 121. And our denominator stays the same. So this is the y value of our vertex. Negative 121 over 4. So then we can go back, and now that we know where this parabola is going to start, we know that the range, because it's concave up, is from negative 121 over 4 going up to positive infinity. Okay, letter 6, or number 6, I'm going to sketch myself a little graph so I can see exactly what's happening here. This is a square root function, so I know it's going to have a shape sort of like this with an anchor point and sort of heading out in one direction. To find the zeros, remember that the 0 occurs when y equals 0. So I will set my whole thing equal to 0, and I will solve for x. First, I'll square both sides to get rid of that square root. So I get 0 equals 2 minus x, and then I'm going to get x by itself. Subtract 2 from both sides, and I get negative 2 equals negative x, and then we can divide both sides by negative 1 to get x positive and by itself. So x equals 2. So I know that at 2, I'm going to have my x-intercept. So 0 is at 2. The y-intercept occurs when x equals 0. So what I'm going to do is I'm going to plug in a 0 for x, and solve for y. So this just gives me the square root of 2, which is going to be between 0 and 2 somewhere. It doesn't have to be exact, but square root of 2. You can put this in your calculator if you want to kind of see the decimal to see where to graph it, but please leave your answer as the square root of 2. So I know my y-intercept is going to be somewhere here at the square root of 2. And then that shows me the shape of this function is going like this, because it's going to have a horizontal reflection, but I don't even need to know that because I have 2 points and I know the shape of a square root function is going to look like this. So my domain, then x values coming from negative infinity until I hit that x-intercept at positive 2, we include it because that positive 2 is a closed circle, so it's included in our domain. And then our range from low to high, the range starts at 0 and continues to positive infinity. All right, and behavior in extrema. So follow the directions, identify the absolute max min, relative max min, where it is increasing, where it is decreasing, and then write end behavior in full notation. So if we start with number 7, the absolute max on this does not exist because it has arrows that continue upward forever. So there is no absolute max. There is an absolute min at D. That is the lowest point on our function. There's a relative max at both B and F. Those are little places where we have a max. They're not the absolute because of these arrows, but we have 2 relative maxes. So we would say B and Relative min, those would be all the points that are not an absolute min. So we have relative min at A and G. And then where the function is increasing. So thinking of our roller coaster and using proper notation. So it is increasing from here to here and from here to here, and then again from here to here. So in proper notation, from A to B, U, from D to F, U, G to infinity. So those are increasing intervals. And then decreasing intervals are going to be, if we think of our roller coaster, where we are going downward. And we'll use our letters to write this. So decreasing from negative infinity to A, U, B to D, U, F to G. Okay, and then end behavior. So talking about where the function is headed in either direction. To the left, as x approaches negative infinity, we look at this arrow to talk about where the function is going. So f of x is approaching positive infinity. And then to the right, as x approaches positive infinity, f of x, looking at our right arrow, also is approaching positive infinity. All right, number 8. Looking at this graph, there is no absolute max because we have this arrow that is continuing up to infinity. There is also no absolute min because we have no absolute minimum value because it is continuing forever to negative infinity. So then a relative max, we have 2 at both D and F. Relative min, we have 2 as well at, 2, B and E. Notice G is not a relative min because there's no change of direction happening. So only at B and C do we have relative min. B and C. Okay, so then in terms of increasing and decreasing, let's start with increasing. We're increasing here and we're increasing here. So left to right, we are increasing from B to D, U, E to F. That means we are decreasing on all the other intervals. So from negative infinity to B, D to E, and then F to infinity. So let's write that. From negative infinity to point B, we are decreasing. Then again from D to E, then again from F to infinity. Okay, and behavior to the left, as x approaches negative infinity, we look at our arrow, f of x is approaching positive infinity. And then to the right, as x approaches infinity, looking at our arrow, f of x is approaching negative infinity. Okay, flip your page. On the next page, you can see that you have a equation, you have a function, but you do not have a graph of the function. So you still need to tell me these things, but using what you know about algebra. First of all, we know this is quadratic. We know it is concave up. So we know that there is an absolute min. There is not an absolute max because this is concave up because our A is positive. So we know there will be a min, but not a max. So let's calculate all of this stuff. Let's do the absolute min. Remember, we need the y coordinate of the vertex to find the absolute min. So let's start with the x coordinate of the vertex, which is negative b over 2a. So negative 6 over 2 times 1, which is negative 3. So our x coordinate is negative 3. To find the y coordinate, we're going to plug it back in. So negative 3 squared plus 6 times negative 3 plus 2. 9 minus 18 plus 2 means that the y coordinate of my vertex is going to be at negative 9 plus 2 is negative 7. So my absolute min is at negative 7. You can give me the ordered pair, but we only need the y coordinate of the vertex for the absolute min. Okay, the x-intercepts, we find those by factoring. We have 2 and 6. These don't factor, so if we can't factor, we must use quadratic formula to find the x-intercepts. Negative b plus or minus square root b squared minus 4ac all over 2a. Plug in what we know. Negative 6 plus or minus the square root of b squared. 6 squared is 36 minus 4 times a times c all over 2 times a, which is negative 6 plus or minus the square root. 36 minus 4 times 2 is 8. 28 over 2. 28 can be split into the square root of 2 times the square root of 7 and square root of 4 times the square root of 7. Square root of 4 simplifies to 2. So we get negative 6 plus or minus 2 root 7 over 2. And then we can simplify. So these all contain something divisible by 2, so we must divide them all by 2. This becomes 1, this becomes 1, this becomes 3. So negative 3 plus or minus the square root of 7. That is where my two x-intercepts. One will be at negative 3 plus the square root of 7. One will be at negative 3 minus the square root of 7. Then our x-intercept, or our y-intercept, sorry, this is in standard form, so we can see the y-intercept is at positive 2. And because we know the shape of a parabola, we can identify the end behavior based on knowing that it's concave up. So as x approaches negative infinity, this is to the left, our function is approaching positive infinity, concave up. And as x approaches positive infinity, so to the right, our function is approaching also positive infinity. All right, now we're talking about continuity. Is a function continuous or not? If it is not continuous, you need to tell me the type of discontinuity and where it occurs. So there are three things we're doing: continuous, yes or no, the type of the discontinuity, and the location of the discontinuity. So number 10, if I trace this with my pencil, it is not continuous because I have to lift my pencil to get to the other part of the graph. So this is not continuous. And I'm talking about the x-axis here when we talk about discontinuities along the domain. We have an issue at negative 4. And because this is an asymptote, we're going to say this is an infinite discontinuity at x equals negative 4. And that's how your answers should be written. Just to do a little more practice with end behavior, as x approaches negative infinity, so we're heading this direction, our function is now approaching an asymptote. So we need to say as x approaches negative infinity, our function is approaching positive 2. And then also to the right, as x approaches infinity, our function is approaching the asymptote of 2. All right, number 11, is this function continuous or not? Well, we can see multiple places where we would have to lift up our pencil to be able to draw this function. So it is not continuous. In fact, there are two places where we have discontinuities. We have a jump at x equals negative 4, and we have a jump at x equals 0. So two discontinuities, not continuous. Number 12, we just have this polynomial function to the fourth power, x to the fourth plus 3x squared plus 9x minus 13. Is this function continuous? Well, you might be like, I can't see a graph. I don't know. So we look for our red flags. Do we have a piecewise? No. So we're not going to have any jumps. Do we have an x in the denominator? No. We don't even have a denominator, meaning this function is by nature continuous, just a polynomial with no domain restrictions. So it is continuous, and we don't have anything to say about the type or location of the discontinuity because there are none. Number 13. So we're looking at this function. The first thing that we hopefully notice is that we have a rational function. We have a denominator with an x in it that is going to give us an issue somewhere along the domain. So what we always want to do when we see this so that we can identify the type and the location is to factor both top and bottom. So if I factor this, 7 and 1, so in factored form, it would look like this. over x minus 3. What this tells me is that I do not have a common factor in the numerator and the denominator. So the denominator solo is going to be my discontinuity problem. And because it doesn't have a common factor, we know that it is an infinite discontinuity. It will be an asymptote. So this is not continuous because we have a denominator issue. To find out where we have it, we take our denominator, x minus 3, set it equal to 0, and solve. This tells us where the discontinuity will happen, which will be when x equals 3, because when we plug in x equals 3, we get a 0 denominator, which means we're going to have an issue on our domain. Okay, 14 is a piecewise, so we need to determine whether or not it's continuous at that point. So whatever you're given in your piecewise, that's the one you want to plug in to see whether or not the function is continuous. If I plug in 3 to my first equation, 2 times 3 plus 1, so I get 5, no, 2 times 3, 6, plus 1 is 7. And then my second one says if x is greater than 3, then y is 7. That means these are equal. What this would look like on graph is if we're doing everything less than or equal to 3, 1, 2, 3, here we would have a closed circle at 3, and this function is going to be sort of coming up something like this. And then this other function is saying greater than 3 is always going to equal 7. So we'd have an open circle over the closed circle, and it's going to continue this way. This function is continuous. We could draw it when we get to that 3. We have a closed circle there that's going to continue. So we have a continuous function at 3 in that piecewise. So there is no discontinuity. Number 15, hopefully you notice that we have a rational function. We have a denominator issue. Before we figure out exactly what it is, like we can figure out where it is, but we want to first figure out what it is. So what I'm going to do first is factor top and bottom. So 2 times 2 is 4. So 4 and 1, because we had this a value that was not 1, don't forget to divide. So on top, we get x plus 2, 2x plus 1 over x plus 2. So now we can see, because we did our factoring work, that we have that common factor in the top and the bottom, meaning we will have a removable discontinuity, which is also a whole, to figure out where we have our problem, we take this denominator, set it equal to 0, and solve. And that tells me where we're going to have our issue. So we'll have a removable discontinuity when x equals -2. And it's removable because we have that common factor in the top and the bottom. Number 516 is another piecewise. So we're going to evaluate at -1 what's happening. Is the function going straight through at -1, or is it jumping? So we'll do that by plugging in -1 to both equations. Don't forget your order of operations. This goes first. So 3 minus -1 squared is 1. That gives us 2. And then we'll plug it into the second. Absolute value of -1 plus 5 plus 1. This gives me absolute value of 4 plus 1. Absolute value of 4 is 4 plus 1 is 5. These two do not equal one another, meaning on graph what this is going to look like when this 3 minus x squared is heading towards -1 of an x. So here's our -1. It's going to look something like this. I don't know, with the whole. And then when we have the absolute value of x plus 5 at -1, it's going to be a closed circle, and it's going to look like something like this. So we have this jump at -1 because something different is happening on each function at -1. So is this continuous? No. We have a jump when x equals -1. And finally, number 17. If x equals x minus 2 over x squared minus 4, we have an x in the denominator in a rational function. So we are going to need to identify issues on the domain. Start by factoring top and bottom. Difference of squares, don't forget that. We have a whole or a removable discontinuity, so it's not continuous. If we set this equal to 0 and solve, we have a removable discontinuity at +2. And we also have another issue in our denominator here still, which we need to account for. This does not have a common factor in the numerator, meaning it's going to be an infinite discontinuity or an asymptote when set it equal to 0, solve. So we will have an infinite discontinuity at x equals -2. So there are two issues on this domain because we had two factors in our denominator. So we have to account for both of them when we identify types and locations of discontinuities.